Welcome everyone. It's a great pleasure to have Stefano Casertano here today. Thanks a lot for accepting our invitation. Stefano is a faculty member at the Space Telescope Science Institute, where he has been since 1994. He completed his undergraduate and graduate studies at the University of Pisa and the Scuola Normale Superiore in Pisa. He then held postdoctoral positions at the Institute for Advanced Study in Princeton and the University of Groningen. Before joining the Space Telescope Science Institute, Stefano held faculty positions at the University of Pittsburgh and University of Illinois. His scientific interests cover several key areas of astrophysics, including the cosmic distance scale, microlensing, rotation curves, and galactic structure, as well as space instrumentation detector development. Today, he will present the Distance Network, a new framework for a robust and accurate determination of the local Hubble constant. Stefano, please, you can start when you're ready.
Thank you very much. Thank you all for coming. Thank you, Eleonora, for inviting me. And I'm happy to be here and tell you about this idea that came up about 2 years ago and slowly developed of having a so-called distance network, which is meant to be a new framework for a robust and accurate determination of the local Hubble constant. And this is the result of work done by a large collaboration, about more than 30 people, and I'll be mentioning this in detail. So this particular crowd has very, very little need of a reminder of why people care about H0 and how H0 creates a connection between the local and the distant universe. We can measure H0 locally using direct measurements of distances in various ways, which we'll describe, and measure redshift, so giving us a local value of the Hubble constant. And of course, the cosmic microwave background can be measured and give us information about the early universe, and with a scale set by early physics. And those two determinations happen to not quite agree today. So one of the more recent values for the cosmic background prediction is 67.24 kilometers per second megaparsec. The current values, which I will describe from the local universe, are closer to 73.5. So the idea of the local distance measurement of H0 has been around for very long, and it's usually described as a local distance ladder, where you take several steps which bring you from the immediate universe, where you can actually measure distances directly by geometric means, all the way to the Hubble flow, where the velocities, the redshift, and the distances are directly related. So in one representation, for example, the first rung would be the geometric parallax measurements of Cepheids, which tell you how bright Cepheids are in various systems, including the Milky Way, in the large and small Magellanic Cloud and NGC 4258. Then you can measure Cepheids in the local universe out to 40 megaparsecs, and that way determine the luminosity of type 1a supernovae, and then move to type 1a supernovae, type 1a supernovae which are bright enough to larger distances and into the Hubble flow. Starting in 1990, but of course the whole idea started much earlier, but the HTK project brought the accuracy on H0 to about 10% using with too early HST instruments. But then since then, we've had various improvements in both technology and survey techniques and analysis as well, like the new instruments on HST, JWST, which has improved the resolution in the near IR, better geometric distances for both for Milky Way and for nearby galaxies, and large-scale supernova surveys. So let me just spend a few minutes just talking about a project that I've been involved in since the beginning, since 20 years ago, the SHOES project, which has been approaching 1% accuracy in the local measurement of Hubble constant. So one example of our distance ladder, this was the paper published in 2022, which was a bit of a milestone for us. In the first rung, we have these three steps in which the first step gives you the measurement of objects that then form the basis for the second step. And you'll hear about these three steps many times today. And so for the first step, we have 4 geometric anchors, Milky Way, large and small imaginary cloud, and NGC 4258. We also have M31, which we do not include as an anchor, as a formal anchor, because it's not quite as accurate as the others. Then in the second rung, we have Cepheid variables, which are measured in near infrared and visible to remove the sensitivity to dust. And then we measure them in 37 galaxies, which include 42 type 1a supernovae, within a distance-limited sample out to 40 megaparsecs. And then in the third rung, we use a large compilation of supernova data. We match galaxies in the supernova host to the supernova host in the local universe, and we determine then the Hubble constant. We have spent a lot of effort making the analysis as comprehensive as possible, carefully considering error propagations, including covariances, systematics, and validation of all the key steps. For example, separate analysis of crowding effects, separate analysis of Cepheid phase, Middle-Easty, host mass dependence, and so on. And we've been very careful always to release all of our data and our code. So everything is out in public. Just a few more details just to show the kind of detail level that each of these measurements can achieve. For the geometric calibration of Cepheids, we actually use many different methods, and they're all in agreement. In this plot, you see Gaia parallaxes for field stars, Gaia parallaxes for clusters, Cepheids in the LMC, Cepheids in the SMC, and Cepheids in NGC 4258. And every single Cepheid in this plot has been measured. These are not all individual Cepheids, they are collected, but all Cepheid in this system have been measured with HST. So all the photometry measurements are in the same system with the same instrument as they are in the distant universe. And as you can see, the dispersion of it's very well constrained. For the Cepheids measured in supernova hosts, these are the collected light curves for every single one. They all are very, very well-defined light curves. And these here you can see the host period luminosity relation based on the Wesenheit magnitudes and with the infrared and visible wavelengths. And again, these are in very good agreement, or very well described by linear period luminosity relation. And then we put it all together. We include all the covariances between objects because of Middle-Easty effects, because of background effects, because of any other effects, same anchor, etc. And we attained the value of 70.04 plus or minus 1.04, which includes systematics. And this is the value from 2022. Now, SHOES is not the only player in this game, obviously. There have been a lot of people, a lot of groups that have measured H0 in many different ways. This is a compilation that was done by our host, Eleonora, a few years ago. But of course, we can produce a new one just about every month with new numbers and new values of various kinds. So the top here are the measurements that depend on the early universe. They're mostly on the pink bar, which is the value from CMB with its uncertainty. The middle ones are the measurements, the direct measurements in the local universe, which mostly lie around the blue bar, which is a value for it from the 2020, I think that's the 2020 value, but it doesn't matter. It's one of the local values. And some of them do deviate a little bit, but in general, they're all around this place. But the problem is, how do we compare these? How do we put them all together? The problem is that many of these measurements share the same data. They may share the same set or overlapping set of supernovae. They may share the same Cepheids or the same distance measurements of various kinds. They may share various types of methodologies. So they overlap in many ways. They all have covariance. They cannot be averaged directly. So the question that came up is that I asked myself, or many of us asked ourselves in the last couple of years, is how can we combine all these measurements into a single, robust, and reliable value of H0? Well, let's figure out what are the pieces that we use mostly in the local measurement of H naught. This is not a complete list, but it covers most of the recent measurements. So the building blocks for distance ladder, as I said, are the geometric distances to the anchors. The anchors are the objects in our immediate neighborhood that you can measure the distance to directly. Well, it's 4250, NGC 4258. It's a little bit further, but it happens to have this mega maser that allows you to measure the distance geometrically. So these are direct distance measurements for individual objects or systems that are fairly nearby. So Milky Way, LMC, SMC, NGC 4258. Then there are what we call the calibrators. So the systems in the second rung in the description before, out to about 40 megaparsecs, which we cannot measure directly, but we can measure the distance to based on the anchors. And the methods we use for that include, for example, Cepheids, include a tip or a branch, which I'm not going to get into a lot of the detail on individual methods here, because for reason of time. And more recently, the J region of the asymptotic giant branch Maya variables. And then we need to make the final step to the third rung in the Hubble flow, and that we do by using secondary distance indicators like type 1a supernovae, the luminosity of surface brightness fluctuations in galaxies, the luminosity velocity grid relation of Tully Fisher. These are all predictors of luminosities of objects you can see in the Hubble flow, and the fundamental plane of elliptical galaxies, which is a predictor of luminosity, which is a relation between luminosity size and velocity dispersion. So these are all objects that you can see in the Hubble flow. So, but these elements can be combined and are combined by different groups in many different ways. And so there are many combinations that are possible. They're, of course, not independent because they contain a subset of the same elements. And then there are also additional methods that completely bypass or change the distance ladder. So, for example, there are an additional 5 megamaser systems for which you can measure the distance to directly using the VLBA. There are models of expanding photosphere for type 2 supernovae, which can measure the estimated distance to individual supernovae directly, not based on any of the previous steps. Then there is the case of the fundamental plane that is calibrated using the distance to coma, because coma has a lot of elliptical galaxies, but the distance to coma can be determined using supernova 1a, and so it becomes sort of in the in between the second and the third rung in that sense. So in order to take this all into account, we basically have to think not of a distance ladder with individual steps that are well separated and well defined, but of a distance network, which connects all these things, all these elements in complicated ways. So for this purpose, we decided that this required a community effort. There are so many different pieces, so many different pieces of expertise that are needed, and we wanted this method to be developed as a community method. So some of us put together a proposal, which was approved by the International Space Science Institute, and we arranged for a workshop which took place in March of this year. We invited experts from all the leading techniques, and many of them attended. We had a total of 37 participants with a response more than 80%. And we thank very much the International Space Science Institute for their hospitality and for enabling this, which was the first step in this work. There's a website where information on the workshop is available. So what were the goals of the workshop? We basically wanted to have an interactive, consensus-based evaluation of all the distance measurements that were available, all the pieces of distance measurements that were available. We wanted the experts together, both the experts in that method and the experts in other methods, to scrutinize each of the methods, identify commonalities, discrepancies, validation strategies, understand how we can use each method to validate others and to compare with others and see where potentially issues are, build a common framework so we can put this all together into a unified analysis, produce a code that could be made available and shared and with a data repository so that this method could be made transparent. and prepare for future extensions, because probably there will be new data. In fact, there already been new data since the workshop happened, and there will continue to be new data, and we will want to include those data as well, together with all the previous data. So we had this 1 week meeting in person, and then we had extensive follow-up work to refine the code, approaches, etc. And we submitted a paper a month ago, which is shown here, with a title that's not a surprise, since you heard the title of this talk, and there's a list of the authors here. Now, I've said a lot of words about all these various methods, but this is a more graphical way to put it all together. So this essentially are the combination of the 3 rungs and the methods to go from one rung to the other. So on the left, you have the anchors and the geometry. And these are essentially the foundation. Basically, they determine the basic scale. Then you jump from that to the nearby universe using the tip of the red branch method, the J-regeneration branch method, the Myras and Cepheids. And the various colors identify either collaborations or methodologies that have been used. So there's a little bit of a mix. And then again, as I said, we'll get to the next step, which is essentially into the Hubble flow, using surface matter fluctuations, using fundamental playing, type 1a supernovae, type 2 supernovae, a Tully-Fisher relation, and direct measurements as well. There should be a one for masers as well. There it is. And all of these bring us to H naught. So that's sort of the high level view of this connection. And you can see now how intricate all these lines are, how much the pieces rely on each other, and how much they interconnect. This is why it's not a ladder anymore, it's a network. So I'm going to spend a couple of minutes just give you a little bit more in-depth description, so so you can see the pieces that go into actually putting this together in a statistically valid and rigorous framework. So the distance network, in its realization in both in code and in the underlying statistical parameters, is constituted of equations that relate data and optimizable parameters. The optimizable parameters are the distance moduli to all the host and calibration galaxies, those in the second rung. The distances to Coma, Virgo, and Fornax. Virgo and Fornax are important because they are hosts to galaxies used to measure surface magnitude fluctuations. Calibration parameters, the reference magnitude for type 1a supernovae, reference magnitude for surface magnitude fluctuation, for Tully-Fisher, etc., and the Hubble constant itself. These are the parameters to determine. Now, the equations that determine these parameters, that are used to constrain these parameters, will put one or more of these parameters in relation to each other and to measurements, to the actual data. So we include this data include the estimated distances to host and calibrated galaxies based on any of the methods before. The calibration equations that relate the calibration parameters, reference magnitude, type 1a supernova, etc., to individual systems, individual supernovae measured or in hosts that are measured with Cepheids. That applies to both type 1 and type 2 supernovae, or the apparent magnitude of surface magnitude fluctuation target galaxies in a galaxy with an estimated distance, and so on and so forth. And then there are constraints on Hubble constant that come from measured tracers in Hubble flow with estimated distances and redshifts, as well as direct measurements from astrophysical measurements. The complexity of this problem comes from covariances. Now, covariance is often considered to be a bit of a dirty word. We try to ignore them as much as possible, but in this case, it's really, really not possible. Covariances are key to understanding how these measurements relate to one another and how they can be used properly together without double counting and taking into account all the correlations between measurements. So without including covariances, measurements will be double counted and uncertainties will be underestimated. And in fact, the system may not have any valid solution. Some covariances arise from measurement sharing. that some measurements may share the same anchor. Multiple Cepheids period luminosity relations are related to the Milky Way, so they all share the uncertainty in the distance in the Milky Way. Other measurements are Cepheids measurements can also be related to the LMC or the SMC, so they share the uncertainty in the distance to the LMC and the SMC. They also share the uncertainty in the period luminosity relation in the LMC or the SMC. So these are all covariances that need to be taken into account, because if you don't and you average things together, you're essentially double counting measurements. TRGB distances also share the apparent magnitude of TRGB in NGC 4258 because they're all related to NGC 4258. That's the only system for which that has been used. Other systems could be used, but at the moment, the only system that has been used to measure distances using the tip of the red giant branch relates to NGC 4258. And all of these covariances have to be included explicitly in system equations. There are also covariances that are due to shear quantities. Like, for example, if you have multiple supernovae in the same host, those supernovae all use the host distance, but the host distance isn't common, so its error needs to be included correctly. And these covariances are inherent to the equation design, so they don't need to be tracked explicitly, but they will be tracked by the system. And then when you have the whole together, the least square solution will yield estimated errors and covariances for all parameters. Now, I don't expect you to really read this equation, but this is a graphic representation of the matrix of equations on the left and of the covariance matrix on the right. And basically, this is just a standard linear algebra problem. There are some approximations here, which I will mention in the end, but it's a pretty straightforward linear algebra problem. The problem is putting it all together correctly, so building the pieces correctly. Once you do that, the problem is trivial. And the solution will give you also not just the best value, also an uncertainty that is statistically rigorous and correlations. The code has been originally written in IDL because that's what well, I personally am most comfortable with, but it's been ported to Python for broader accessibility. It is highly flexible. It is driven by configuration files or command line parameters, so you can include or exclude any subset of data. The data format is very simple, just ASCII files, and it's the data are directly derived from published tables. And we can include or exclude them as desired. There's also the ability to export the results of internal calculations and intermediate results in diagnostic output, so we can look into how things are working and why. The code and the data are being maintained on GitHub. At the moment, they are private to the group, but they will be made publicly available as soon as our results are published. All right, there are a lot of measurements, as I said, but not all measurements have the same pedigree. Some of them are more recent. They may have been tested less. And in keeping with the idea that this was a community effort, we asked participants to the workshop to basically assess their level of confidence in various types of methods, including primary distance indicators as well as secondary distance indicators and tracers. Vote was anonymous. It was taken before any calculations were carried out and made public, so the result, it's not influenced by the results. And these are the summaries, basically, for the primary distance indicators and the anchors, the Cepheids, detached eclipsing binaries, and Gaia parallaxes, and NGC 4258 and tip of the red giant branch were all almost unanimously considered to be a baseline. But other methods like MIRAS and JAGB were mostly considered to be suitable for variance. No method was actually excluded in the end, although there was also a possible vote. As far as the secondary distance indicators, the type 1a supernova, surface magnetic fluctuation estimates of brightnesses, and the Masers and Hubble flow were all considered by a majority of the people to be baseline worthy, while other various methods of measuring distance to type 2 supernovae, the fundamental plane, and Tully-Fisher were actually then put in the variance. I will say more about the variance later. So this vote happened the first day of the workshop. How things look like? Well, so I'm going to show some of the consistency tests we made internally. For example, this. Am I okay? Because I'm getting a message that the internet connection is unstable. Are you seeing everything fine?
Yes, perfect.
Okay, thank you. So here, for example, this plot shows individual hosts measured with different methods. So, for example, in this area, you see all the hosts measured with Cepheids, measured with Cepheids with the Hubble Space Telescope, with reference to the Large Magellanic Cloud. And so you can see that the individual Cepheids have error bars due to their individual, period luminosity relations for Cepheids for individual galaxies. Have their own internal uncertainty, but there is also a global uncertainty that's based on the fact that the distance in the anchor and the uncertainty in the period luminosity calibration in the anchor, that's a gray bar. So when you look at these points, the individual diamonds are supposed to scatter by the error bars around this mean, but the mean itself is also has this, what you might call in this context is a systematic error, but in fact it's not systematic. It's just from the fact that they share the same information. The next set is the Cepheids measured with HST, but reference to the Milky Way. That's a little bit different. The third is Cepheids measured with HST, but reference to NGC 4258. Then you have the JWST measurements of Cepheids, which are many fewer, and they're all referenced to NGC 4258 because we do not have JWST measurements of Milky Way or LMC or SMC Cepheids, so we could not make the relation there. The next is the Chicago Cosmology Project measurements of TRGB with HST, reference to NGC 4258, and so on. So basically, for each subset of objects measured, of galaxies measured with the same method, a reference to the same anchor, this shows how the group scatters internally and how the groups scatter with respect to each other. And you can see that there is nothing really particularly big here. I mean, this the range here is tick marks of plus or minus 0.1 distance modulus, and just as a reference, the difference between the local and the cosmological measurements of H naught is about 0.17 in the scale, so we'll be around here. Similarly, you can look at objects, tracers in Hubble flow. And again, these are individual tracers, the systematic error bar, as well as individual measurements. And of course, as you go to very low redshift, there is a significant uncertainty coming from peculiar velocities, which is shown here in gray. So everything looks okay here in these various residuals. So once we put it all together, now this is the baseline solution. So in the baseline solution, as defined by the vote, that includes anchors of Milky Way, the LMC, and NGC 4258. SMC was not included at that time, it came in a little bit later. Includes all Cepheids and TRGB measurements of for primary distance indicator. It includes the type 1a supernovae and TRGB calibrated surface magnetic fluctuations and megamaser distances. And the type 1a supernovae are taken from Pantheon Plus. And at this point, there are 55, 13 more than the 42 that were considered in the 2022 paper by Schutz. So we have increased the number of supernovae available, thanks to the fact that some of them have distance measured with TRGB. And the result of this is very, this would be, basically our endpoint, if you will. H naught is 73.47 plus or minus 0.80, an error that's a little bit larger than 1%, but not much. It's about 7.1 sigma away from the value of the CMB plus Lambda-CDM that I showed before. And if you look at the internal discrepancy of the points, basically the chi-squared, because this is a chi-square problem, the chi-square per degree of freedom is 0.987, which is almost too close to 1. It's a very, very good, very, very much what we expect. We also show here the covariance between some of the determined parameters, not all of them, because individual hosts, there are about 45 different measurements of host distances, and that would make for a very large and very uninformative plot. Individual hosts don't carry a little weight. One thing you can notice is that there is a pretty strong correlation between H naught and the calibration, the absolute magnitude of type 1a supernovae. They're strongly correlated because type 1a supernovae carry a lot of weight in determination of H naught. There is also a fairly significant correlation between the surface matter fluctuation calibration and H naught. Similarly, because also the surface matter fluctuation carries a fair amount of weight. Sorry. Okay. Now, this is the baseline. What about all these variants? What are we doing with all these variants? Well, the underlying question of the variance is, now we understand how to put together everything. Can we break H naught? Can we show that something is wrong? Can we see something that is not consistent? Is there a problem somewhere? And so for that purpose, we adopted, well, 4 classes of variance, essentially. Add one method, where we take a baseline, and by the way, this is, of course, the whisker plot of all the variants compared to the baseline, which is the pink bar and the top line. So first, try to add one method at a time to the baseline. Doesn't make a difference. Leave one out. Take out some subset of data with common properties. Instrument-driven, exclude the instrument platform, or alternate, modify elements of the analysis. And also we put in a solution that includes everything. One thing we agreed on, the participant in the workshop agreed on, is that ad hoc exclusion of selected objects or data is not a valid variant. You have to have a reason, either a coherent group of data or some hypothesis on something being wrong that drives that, because otherwise picking and choosing individual objects for exclusion is a recipe for disaster, because anything can be done if you can pick and choose what you include or what you exclude. So that was a very important driving principle for us. So let me go through these various groups of variants one by one. So add one method. This basically added one at a time the regional asymptotic giant branch as an extra primary distance indicator, Myers as an extra primary distance indicator, the fundamental plane of elliptical galaxies as an extra tracer calibrated to the coma distance, the empirically calibrated type 2 supernovae, basically type 2 supernovae calibrated like we do for type 1a supernovae through host distances. Type 2 supernovae calibrated using models of expanding photospheres, and Tully Fisher. And then the last one is including the small imaginary cloud as an additional anchor. And you can see that basically all of these methods don't change much. I mean, you don't expect them to scatter by as much as the error bar, because all these methods have very much a lot of information in common. So the bar here is not an indication of the uncertainty for that particular measurement. It's not an indication of what the scatter would be across variants. So that's very important to keep in mind. Although if some variant deviates more than the uncertainty, that is of course noteworthy. Okay, leave one out. So this is a little bit more varied because you can exclude subset of data of common properties in many different ways. So here I've no Cepheid, exclude all Cepheid measurements, only TRGB in the baseline. Remember, the JHB and Myers are not in the baseline. Or not TRGB, which also excludes SBF galaxies because they're all calibrated with TRGB. No Milky Way as anchor. So two anchors excluding Milky Way. No LMC as anchor, excluding all the detached clippings and binaries measurements. No NGC 58 as anchor. No type 1a supernova at all. So this particular variant, there is no information from type 1a supernova. So essentially only baseline, only SBF and Masers and Hubble flow, or no SBF, no surface band fluctuations, or no Masers and Hubble flow. Some of these options result in fairly large uncertainties, because if you remove all Cepheids, you basically are removing a lot of the predictive power of the method. If you remove all type 1a supernovae, you remove even more. The one that deviates the most is the no Cepheid case, and it's in fact worth looking into it a little more deeply. The issue with the no Cepheids is that a number of supernovae that are actually only measured via Cepheids. Therefore, if you exclude Cepheids, you also drop the supernovae, those supernovae from the sample altogether. And that actually has a bigger impact. So the dashed line here, I hope you can see it, the dashed blue line underneath the no Cepheid line is actually basically the distance network solution with Cepheids, but without the supernovae that only have Cepheids. So basically, the dashed and the two blue lines, dashed and the solid, are show the effect of just removing the Cepheids from this measurement, not changing the supernova sample. So all of these deviations are consistent with expectation. In particular, the effect of Cepheids has a significance of 0.3 sigma. So it's not exactly worrisome. Instrument variations. There are essentially most of the data, in fact, everything beyond the anchors has been measured with HST or GWST. So we can remove HST, which also means removing the Cepheids, because there's no Cepheid calibrated with. Sorry, I'm taking back. Also means calibrating Cepheids only with NGC 4258, because we don't have Cepheid measurements in LMCA and in the Milky Way using JWST, or removing JWST, leaving only HST, this is just a test. There are a handful of supernovae, 7 supernovae that were measured before 1994 that have less accurate measurements. So removing those, and again, there is no real variation beyond expectations. And finally, alternate treatments. There are quite a few options there. I'm not going to go through each one of them in detail, but the options, my bad. Options include no peculiar velocity correction, restricted redshift range for tracers, so only closer than 0.06 or further or further. Several different supernova-like curve analysis methods, including the use of near-infrared or in the visible different methods for standardization. Ignoring the covariance between tracers, that's actually a very, very small effect, but we tried that. Removing the Cepheid metallicity correction, this has been surmised by some that there is no Cepheid metallicity correction, so we removed that to see what effect would be. It's very, very small, as you can see, so varies very little. So in some cases, there are variations in the central value with increased uncertainties. But again, I would say none of these is surprising. None of these is worrisome. And finally, we have the everything solution, which includes all anchors and all non-overlapping measurements. Now, it's important to note that we can only legitimately use one measurement for each type of supernova, because some of the deviation of individual supernovae from their typical luminosity may be intrinsic to the object and therefore may correlate across methods of standardization or across passbands. So that those correlations have not been quantified sufficiently, and therefore the only safe thing is for every supernova to include only one measurement. But otherwise, we include everything. And we find that the inclusion of Tully Fisher is optional because the Tully Fisher as a variance is slightly too high. So we think that the error model may need to be refined further. The value of H0 is slightly higher than for the baseline solution, 73.94, with a smaller nominal error. It is less than 1%, in fact. And if you exclude the Tully Fisher, it's still less than 1%, but the value is slightly lower in between. And these are 8.7 or 8.1, depending whether you use or not the Tully Fisher from the CMB value. The chi-square for the Greer film is large if you include Tully Fisher, is more normal if you don't include Tully Fisher. We mean this everything solution to be indicative of future improvements. I mean, these methods were excluded from baseline for a reason, so we don't say, oh, this is not a substitute for the baseline solution. But hopefully, these methods will improve, and in the not very long time, they will be included in. They can be included in a future baseline, and that's what we look at in terms of the accuracy with today's measurement precision. We've done another, I don't know if I have time, but I will just briefly mention there have been other tests. So one of the tests was made is to basically take two subsets of data that are completely non-overlapping, completely non-covariant, but they have similar predictive power, not the same, because some of the measurements have better accuracy than others. But just to try completely separate, and we find one method gives 73.11 plus 5.92. One method that goes 73.45 plus 101.78. So these you would expect to differ by order of their combined error, and they're very, very close to one another. We also looked at each individual set of data we're using, and we try to and we use the distance network formalism to rederive the value that was derived originally by the authors that have published those data. So in most cases, the value is extremely close. We usually cannot do it exactly the same because maybe we have a different anchor value, or maybe there may be other slight differences. But as you can see, the red is our point, the brown is the original, and as you can see, they are mostly extremely close, both in value and the accuracy, with the result of the original paper. There was one case for type 2 supernovae where our selection actually reduces the numbers of type 2 supernovae. So these two, our sample of type 2 supernovae is actually not consistent with the original sample. And if we redefine our sample to be consistent, we also find the same result. So this is not a real difference. So in all cases, we reproduced essentially the value that were originally published. There are a few approximations in this process. I mentioned at the beginning, we were trying to look at the results as published. And so we used the published results. In some cases, we had the results tweaked by the authors. Some in a few small things were changed, but really very, very minor. And so what happens then, if you look at the measurements that are published and they share some components, some of them are redundant. Basically, they're the same quantities, they're just combined in different ways. So in that case, you might end up with results that are not independent. And in fact, the solution knows that, because if the covariances are included correctly, the covariance matrix will be singular, and therefore you will have to reduce your system to take out those redundancies, and that happens automatically in our code. So we don't have to make that decision. As long as the covariances are included correctly, that happens automatically. Also, in this particular representation, we have assumed the errors are Gaussian, and we have linearized all equations in magnitude or log distance. So this is not exactly right. Some of the measurements are linear in distance, some of them are linear in log distance, but the uncertainties are small. And the reason to use only Gaussian errors is in most cases, we do not have the full probability distribution function for measured quantities. So we could not do anything more. Sometimes people publish asymmetric errors, but that's not enough. If you really want to do better than Gaussian, you really want to have the actual probability distribution function. And so at the moment, we can't do any better than this, really. And linearization errors themselves are typically negligible at the type of uncertainties we have. But we expect the future developments could drop those assumptions. And if possible, we would want to include PDF measurements. Also, one thing that we did in this case is we started from combined values. So, for example, we did not use individual Cepheids. We used the period luminosity results from fitting Cepheids in the original papers. In principle, you could go back further, but again, that's not always possible. In some cases it's possible, in some cases the individual photometry is not being published, so you can't do that. You can only use what is being published. So in that sense, all the treatment of all the data that we have has been consistent. Nothing has been done differently for one set versus another, but we have had to resort to what was available publicly for all the data. So let me, it's been a long slog, so let me just go to a summary. What we have done is, you can describe it as a bit of an experiment in trying to cross, trying to create cross bridges between different subsets of a large community. So with this method, the distance network, we have tried to, and we have in fact created a framework that enables a unified and rigorous combined analysis of nearby distance data. The method is highly flexible, it's customizable, lots of options are available, and we have run very many different tests. We have made comparisons to published results. We have not found any significant discrepancy. We wanted to try and see if we could break H0. We have not been able to break the local value H0. And of the many variants considered, and you've seen the breadth of variants that we've considered, they all yield an H0 value between 72.5 and 74 kilometers per second megaparsec, all within essentially one sigma of the baseline result, or maybe 1.1 sigma. So the conclusion of all this is that the local value of H0 is very robust to data selections and to analysis choices, and the discrepancy with the cosmological value is confirmed and strengthened. Also, the distance network framework is the distance network is a framework that actually we can use in the future. It's powerful, but it's expandable. It's transparent because the code is going to be public, and the data are going to be public. They're all published, and so we will be able to incorporate new data as they become available. We plan to expand and maintain the code base as needed, and then future measurements can be evaluated within the same framework. And as a final remark, is that this whole fun with attention is unlikely to end anytime soon. And thank you very much for your attention.
Thank you for the very great talk. Do you have any questions? Levon, yes?
Yeah, thank you very much. I really enjoyed your talk. It was very clear for a theorist like me. Very clear. Thank you. I was curious to know your opinion about this recent claim of progenitor age bias. I don't know if you noticed this paper. They claim a strong correlation between standardized supernova magnitude and progenitor bias, essentially saying that all the galaxies have supernovae of different magnitudes. I don't know if you have not seen it, that's fine. I was just wondering if you have.
I've not seen this paper. I recall back in around 2018, there was a big discussion about supernovae, their relation of supernovae properties to the galaxy in which they are. And so there was a very detailed analysis of that potential discrepancy. So I'm not familiar with this newer claim, and I have to admit that I'm not particularly a supernova expert myself, but I would expect that it will be looked into very soon. Thank you.
Thank you.
But again, if we remove all supernovae, the result becomes less accurate, but it doesn't really change. So any systematics that are inherent to type 1a supernovae specifically can be tested with this framework. So I think that's one of the powers of this framework, is that, okay, you ask a question, what about supernovae, and you take out the supernovae and you get the result, and you see what changes.
Thank you.
Thank you. Sayanta?
Okay, thank you very much for this nice talk, actually, from observational point of view. I just had a very small question, in a sense that, I mean, as I understand that it is very much like the anchor toward the local observation, right? Like the later. So I am asking that, are you aware that whether for the other spectrum of the Hubble tension, that is the high redshift for CMB or like the bisafe size, because lots of are working on the CMB, is there a similar anchoring possible? I mean, based on the ladders, I mean, is there how should I say, effort from the early high Z people about this anchoring? I mean, can it be generalized for that? So I was just wondering about that.
Yeah, so I'm not sure if I understand the question, and I have to admit I am not an expert on the on the cosmological measurements, but there are some basic parameters, like for example the sound scale that drive that measurement. So, but again, this is not something that we're looking into in this particular analysis.
Sure. Thank you very much again for the nice talk.
Thank you.
Thank you.
My name is Susana Landau. First of all, thank you for the very nice and enlightening talk.
Thank you.
I have a question regarding the following. At some point, I know that you are always assuming the cosmographic expansion. I don't know if this is common for all the techniques you mentioned, because when you assume the cosmographic expansion, you have to assume some value for the jerk and deceleration parameters, and these values also assume always assume Lambda-CDM. So my question is, in all the tests that you have performed where you excluded at one time data or techniques, if this assumption of the jerk and deceleration parameters were also excluded or if all the estimation of H naught that you showed involve the assumption of these parameters. Thank you.
Yes, good question. The largest redshift of any of the tracers we use is about 0.15. So we actually tried very early in the process, we tried to see if there was any leverage that we could obtain from looking at all these tracers and try to determine the cosmographic expansion parameters. And the answer is no, we don't have any power. So that's another way to say that it actually does not affect the results. So we have tried to make some changes for example, for Q0. And in fact, some of the data that we use adopt slightly different values of Q0. The Tully-Fisher value is slightly different from the original papers, is slightly different from the value that the supernova community uses. But we've done the analysis with a common value of minus 0.55, but it really makes no difference, no discernible difference. So that's why it was not included in official variant, because it really does not make a measurable impact on the results.
Okay, so we can confidently say that there is no Lambda-CDM assumption in all these estimations.
No real Lambda-CDM assumption. There is no dependency of the results and on those parameters.
Okay, thanks a lot.
Thank you.
Thank you. Florian?
Hello, Stefano. Thanks for your talk. So I would ask a very simple question that maybe I didn't get. So what's the difference between the everything solution versus a baseline solution? So in the everything solution, are you using new models, or so?
No,
what's
we
the
just
difference
include more
between
data.
them?
Sorry, I'm sorry. I jumped in. No, the only difference is which data are included. So in the baseline solution, we do not include type 2 supernovae. We do not include the Tully-Fisher estimates, and we do not include some of the secondary distance, primary distance indicators like the JAGB. And in the everything solution, we include those. So,
Okay, thanks.
So basically, it's a more data going to the everything solution. And some of them are considered to be not quite as mature as others.
Thanks.
Thank you. And Karsten?
Yes, hello. Thank you very much for the talk. I have a very simple question. we all know that the TRGB method of calibrating gives much lower values, more around 70. And now if you combine all the other methods with the TRGB method, you hardly see any effect anymore of that method. In other words, like you still get above 73. And is that simply because there is less data this method has, or why does it play such a small role?
No, that's actually, I will slightly disagree. The TRGB method does not yield a different value of 70. It's a combination of elements that arrive to a published value around 70. And they're mostly on the supernova side. They mostly have to do with choices of supernovae, both the supernova standardization technique and the choice of supernovae themselves. But TRGB, it's going to be, allow me to go back to the plot that I showed here. You can see the difference between the TRGB directly when you look at the individual TRGB distances for for essentially subsets of the same objects. These are TRGB measured by Lee et al. These are TRGB measured by Friedman et al. These are TRGB measured by Anand et al. These are TRGB measured in shoes, and they're all very, very close to the zero line. So TRGB itself does not disagree with other methods. If you look at the same host with TRGB and with Cepheids, you will find that the differences are, I mean, there are of course some deviations because the uncertainties are individually large, but it really doesn't, there really isn't a major systematic effect. But once they're combined with a different set of selections, you can have different results.
I
So
see.
it's
So
a
like
bit
it's
of a-
mostly due to the selection they used in these papers.
in the supernova, yes.
Okay, thank you very much.
Selection and treatment of the supernova.
Okay.
Thank you. And Umut?
Yeah, thank you for a very nice talk. So if I understood correctly, you scrutinize the measurements of the distance network. There are other measurements like one-step measurements that are not based on distance ladder, and there was a paper on that. So if you focus on those one-step measurements, their mean is actually low and consistent with Planck. So is there any plan to just expand this to those kind of measurements?
So are you, I'm not sure which measurements you're referring. We do include two sets of one-step measurements, the megamasers and the type 2 supernovae with expanding photosphere method. And those both do not have a significant disagreement with the other methods, but the accuracy or the error bars are much larger. So you could imagine more variation. So I don't know, there may be other measurements that we can include. If there are other measurements that are worth including, of course we would. So if you specify which ones you refer.
I mean, this perivariable Polos paper, Leandros paper, there are like 33 measurements. I think the two methods are the same, but there is gamma ray attenuation, and there's I think there's a few other techniques there. But I think the interesting thing is that there are many measurements there, many papers coming from independent groups. I think you included only 2 or 3 of them.
Okay. Well, again, the plan is to have this publicly available for additional measurements to be included, but we can certainly include the single step measurements. In fact, part of the reason to put together the distance network framework is to include measurements that have different procedures. So you're not required to do a ladder type analysis. Thank you.
Thank you.
We can thank Stefano again. Thanks a lot. Very great talk.
Thank you very much for having me here.